Okay, today we're going to be looking at problem 4.2, problem 2 of chapter 4, and this is a method of joints problem. We have the truss that's given. It has 10 foot panels this way, 15 this way, and the different joints we have in the loading 2,000, 2,000, 2,000, and a 500 pound force here. So we have our pin over here. We're going to go ahead and model this up. Call this reaction RAV. And this guy, if I notice this guy's acting that direction, I'm going to go ahead and model it this way, which I believe is going to be true for RAH. And then I have a roller here tending to turn it up. That's what it looks like to me. So I'm going to call that RCV. So we'll solve the reactions first. Let's look at sum of forces in the X. Have to equal 0. And in the X we have 2,000 minus RAH is equal to 0. That resolves to RAH is equal to 2,000. It's a positive number, so it does indicate that I have that correct. So we go over here to Y. Sum of forces in the Y have to equal 0. In the Y we have RAV up plus RCV up minus 500 minus 2,000 minus 2,000. That will give us RAV plus RCV is equal to a positive 4,500. So we need now to resolve this through a moment. So I'm going to take a moment, summation of moments about any point have to equal 0. Clockwise moments are positive. I'm going to take them at A, and then we'll knock out these guys and this one here. So I'll be left with these. So we look at this, 15 times 2,000, that's a positive moment. Positive 15 times 2,000. And then we have this one, which is 10 times 2,000, that's a positive moment. 10 times 2,000, positive rotation. We also have a plus 10 times 500. And then we're going to have minus 20 RCV, and that's equal to 0. So looks like this will resolve. Doing the math, multiplying those, and bringing them over to the other side, I get a negative 55,000 divided by a negative 20, and that gets us 2,750. It's positive, so that's acting up. And when we plug that into here, we get RAV is equal to 1,750, and that's also positive, so that's acting up. So what we could tend to do, and what I would do, is now that you have your reactions, you can go ahead and put those on your diagram and put those in where they need to go. So we're going to say that C is 2,750. AV is 1,750. And this is 2,000. Now, one of the things I would suggest also, if you make a mistake and you have a negative reaction, don't indicating acting up. Flip him in the picture and then make that a positive. So correct the picture to match what the math is telling you. Okay, so this is very important at this step, because then we're going to go in and look at doing the joints. So as we look at this, there's only a couple of places I would start. There's too many unknowns here, but there's great place here. This is a good place to start, or probably C. So I'm going to start here with a joint diagram at E. Okay, at joint E, we're going to have one force acting down external, one force acting this way external. And then we have two unknowns, one like this and one like this. And as you can see, this is pretty straightforward, because this guy has to be reacting against this to be in equilibrium, and this guy's going to have to be acting in that way. So we're going to call this ED, and this member is EA. So this one should resolve really straightforwardly. Sum of forces in the X have to equal 0. In the X, we have 2,000 minus ED has to equal 0. So therefore, ED is equal to 2,000. And since it's a positive, and we indicated it going ED as going that way, it's a compression member. Joints in compression, so the member's in compression. So now we're going to go to sum of forces in Y. Sum of forces in Y, we have EA minus 2,000 equals 0. Therefore, EA is equal to 2,000. And that one also was indicated correctly, so we called it compression as a guess. It definitely is compression. So that one was an easy one. We like to see those when we have that. So now we can probably go to joint A and work the rest of those from that point. Okay, so now we're going to focus in on joint A and see if we can resolve that. So we do have several knowns and several unknowns. So one of the knowns is the reaction, and we determined that to be 1750. And then we have another reaction that we determined to be 2,000. So we also determined AE to be 2,000 in compression. So that's this vector coming down, and if it's in compression on the top, it has to be compression on the bottom. So you got to make sure that you're orienting that in the correct way. So then we have this guy acting in a manner like that, and this guy acting like that. So we're looking at solving AD and AB. So if we look at the diagonal again, that usually is the one that we can determine the direction on it, and a lot of times this is just a guess. If you don't remember that or don't think about it, you can just act it in any direction. But I'm going to look at this and I can see that these guys are vertically out of balance. This guy has no vertical. So this guy has to have all the vertical. And so since 2,000 is greater than that 1750, this is going to have to be counteracted by that. So we're going to call this AD. And I'm just going to arbitrarily say, I think this is acting like this. If it isn't, I'll get a negative and it will tell me. So I'll know that. Okay, so we're going to start out with the sum of forces in X. Sum of forces in X have to equal 0. So in X, we have AB plus AD horizontal minus 2,000 is equal to 0. So all that really gives us is AB plus AD horizontal has to equal 2,000 pounds. Okay, so we come up here, take a look at sum of forces in Y, and if this doesn't resolve, then we went to the wrong joint. We'll just pick up, go to another joint. So let's see, here we have a dV plus 1750 minus 2,000 is equal to 0. And this is going to give us the value of ADV. So ADV, we add those two together and bring those guys over, gives me 250. And it's positive, so that indicates to me that I do have that right. So now, knowing ADV, we can solve ADH, and if we can solve ADH, then we can solve AB. So we have a proportion here. This is 10 on this side and 15 on this side. So we know that ADH is to the distance over which it acts, which is 10, as 250 pounds, is to the distance over which it acts, which is 15. Okay. Solving that simple proportion, we get ADH equal to 166.67. Plugging that in down to here, that gives me AB. It's going to be equal to 2,000 minus the 166.67, and then that tells me that we get 1833.3, and because it was indicated tension, we can prove that it's positive, so that's a tension member. So the only other thing we need to do is now solve AD. So AD is going to be 250 squared plus 16, or 166.67, excuse me, squared, square root, and AD turns out to be 300.5, and we indicated it as a tension member, and so we call this tension. So that one resolved very nicely, and we can move on to the next joint. If we go back and you look at your initial picture, you'll see that joint B is really very, very solvable, and so that's the one we're going to head to now. Okay, so looking at this now, we're going to go to joint B. Joint B. And at joint B, we have an external load of 500. Don't forget externals, because sometimes that happens with people and that's a problem. So we determined A, B from the last joint to be a tension member. So this has to be tension going this way. And the magnitude of that tension turned out to be 1833.33. So as I look at this, I have an unknown here and an unknown here. And if you look at this again, it's pretty straightforward. If this is going down, this has to go up to counterbalance it by equilibrium, and same thing here. This is going to have to go right. So we're going to go ahead and call this BD, and this is going to be BBC. Okay, so this one should resolve very simply, and our signs obviously should be right as well. So we've got sum of forces in X equals 0. So in X we have BC minus 1833.33 equals 0. And therefore BC is equal to 1833.33, and it's tension. Now you could look at this and probably say that without going through this math, but the minute that you do that, that's going to be a problem. And you need to get into a habit of just doing this in a routine, and that way you will never make a mistake. And if you do make a mistake, then it's easy to go back and debug what you've done. So sum of forces in Y have to equal 0. So in Y we have BD minus 500 equals 0. So therefore BD is going to be equal to 500. And again, that one will also be a tension member. So this one, these are always the easier ones. And so now we can go up and probably take a look at D, which is a little bit more complex. So we are going to have to put a lot together. And then ultimately we'll finish off at C. And hopefully if we get everything resolving to 0, we know that we did this properly. Okay, we're going to go to D now, and D has a lot going on in it. So we have to really focus in on what we've solved and what's going on. So the first thing I'm going to do at D is I'm going to put, we have a external load, 2,000 pounds acting down. We just solved BD, that's a tension member. So that's a tension member at 500. We had earlier solved ED. ED, if we go back and look at that, that resolved into a compression member. So it's acting like this, and that was 2,000 pounds in compression. We also solved member AD, which was the diagonal, and that turned out to be something like this. And that was a tension member, so we've got to make him tension here. And what's most important about this is that you use the two horizontal and vertical components and get them in the right spot. I mentioned that before, but if you put the wrong one with the right arrow, you get a problem. So if I put this, if I reverse them, it's not going to work. All right, so the last thing we have is this guy here, right? And this is our unknown. Now, again, as we look at this, we can see that some things are out of balance. As a matter of fact, if you look at the 2,000 acting this way to the right, this one acting to the left, this thing is going to have to act also, I'm sorry, yeah, to the left. This is going to have to act like that because this component plus that component is going to have to outweigh that 2,000. And hopefully then the other one will work right. As I mentioned before, if you get a negative on one of them and a positive on the other, then something's wrong. And that would probably indicate that you either blown your math earlier on or you blew a reaction. So let's see what we got here. So we're going to start out with sum of forces in the X equals 0. So in the X, we're going to have 2,000 minus 166.67 minus DC horizontal has to equal 0. And so that resolves to DC horizontal equals 1833.33. And it's positive, so that does definitely indicate that it's going in the right direction. Now, if we solve dV here, and it isn't positive, then again, we've got a problem. So let's see what's going on here. And then we also can do a little check when we have the proportion geometrically. So sum of forces in Y, and in Y we have dCV minus 2,000 minus 500 minus 250. And all of that must equal 0 by equilibrium. The sum of those gives me 2750 negative. It's going to come over as a positive 2750. And there's your positive and positive, so that's good. So now we can also do a simple proportion. And we can say that 1833.33 is to the distance over which it's operating, which is 10 feet, as 2750 is to the distance over which it's operating. So if that division doesn't equal that division, you've got a problem. I think you'll do it. If you check it in your calculator, you'll see that it works, so that's good. That pretty much tells me we're on the right track now. We're in a good spot. So when we get to the last one, we should resolve everything to 0 at this point. So let's go ahead and we'll go to the next one and see what we can do with that. Okay, so we are now ready to finalize this. And this is what I call the moment of truth. If this doesn't go to 0, we've got a problem somewhere. So this is joint C. Joint C has everything resolved at this point. We have a reaction. And that reaction was determined to be 2750. We just determined this vector right here, or that member, if you will. We determined that as a compression member. So it has to be compression in this joint. And we need the two components of that, the horizontal and vertical. Horizontal component turned out to be 1833.33. The vertical component was 2750. Then we have this vector that is coming in. That was a tension member. We determined BC to be tension. Tension was also 1833.33. So we're going to look at sum of forces in X, and if you look at this by inspection, you can already see 1833.33 minus 1833.33 is equal to 0. That checks. So sum of forces in Y must equal 0. We've got again 2750 minus 2750 has to equal 0. It does, and there's your answer. So again, this resolves. If you have a problem, if one or both of these don't go to 0, that gives you an error, a thing that you've got to look at. So again, first thing I would probably look at would be your reactions. If your reactions check, then you're going to have to go back through, probably start with your first joint and work it through. And typically you'll find like you blew a sign somewhere, or you considered it this, like for instance, maybe you considered that compression when you brought it in, and so that just carries through. So you have issues like that that happen, and that's the biggest deal with method of joints. But it is foolproof, because if you get zeros, then you know everything's good.